All right, this is my solution to problem 4. We start with our diagram. This is the mass on a spring. Theta is defined positive this way, gives us our little relative reference frame. Theta is in the direction of increasing theta, R is in the direction of increasing R, and then this is an inertial reference frame for reference. So we can define the position of the ball in the relative reference frame as just RER hat. That's just the distance of the ball from the origin. And then we can also, take the derivative of this to get the velocity of the ball in the relative reference frame. I learned it the undergraduate way, as the professor said, so I use these coordinate transforms. They're pretty easy to write out. And basically, when you take the derivative of, say, like ER hat, you get this theta dot out the front, and then your sine flips to cosine, and your cosine flips to negative sine, which lo and behold is the exact same coordinates as E theta hat. So you can just transform that E theta dot R into theta dot E theta hat, and the reverse is true for E theta dot hat. So using those, we can plug that in and get this equation for the velocity of the ball in terms of in time, and then using those same coordinate transforms, we can get the acceleration of the ball across time. So that's pretty straightforward there. Then we can take that equation, our equation for acceleration of the ball, to get the governing equations of the system. So we start with our FBD. Sum of the forces is mass times acceleration. The only forces acting on the ball are tension and the force of gravity. The force of gravity is in the positive y direction, and I set positive y equal to down. And then doing a little coordinate transformation to get it to the relative reference frame gives you this value for force of gravity, and then tension is just always in the ER hat direction, and it's that value negative k minus times R minus R naught. Pretty standard stuff. You plug those back in, and it gives you that whole big long equation right up there, and then we can just break that apart into the ER hat direction and the E theta hat direction. So the ER hat direction, those components are these, and then when you rearrange, you can get the governing equation for R double dot as this. And then doing the same thing in the E theta hat direction, these are those components, and then isolating for theta double dot gives you this equation. So that's part A. Part B, we're looking for the equilibrium point, so that's when R dot, R double dot, and theta double dot are all 0. And so we can start with theta. Just intuitively, to me, that makes more sense. Obviously, from the diagram, the equilibrium is going to be when the ball is just hanging straight down, or if it's balanced perfectly up top. So that's going to be when theta is 0 or theta is pi. And we can see that mathematically when we take these terms here and set theta dot and theta double dot and R dot, doesn't really matter, all equal to 0. This whole side of the equation goes away, and you're just left with negative mg sine theta equals 0. The negative mg doesn't matter because it'll never be 0, so you're only interested in when sine theta is equal to 0, and that only happens at 0 and pi. So intuition and math are lining up, that's good. And then you can plug those coordinates in to this top equation to find out what the R value of that equilibrium point is. Obviously, intuitively, it's going to be when the force of tension and the force of gravity are equal but opposite. So that's going to be in a little bit of a stretch down here and a little bit of compression up top. And then mathematically, we can see that I define the tension term from the spring is just T. So that's when T is equal to mg cosine theta. So you plug in the 0 and pi into theta, and you get some algebraic manipulation, but you essentially get R naught plus minus mg over k is the equilibrium point. And so those are those two coordinates right there. So that's how you do that. That's how I did that. And then on to C and D. This is just a little notation stuff for C because it's mostly code. So I defined the y1 is R, y2 is R dot, all that stuff. And then these are my y1 dot is equal to y2, that kind of stuff. That's all trivial, but these are the equations in how I put it into MATLAB. And then on to D, the energy stuff. The kinetic energy of the ball is going to be its kind of like its swinging motion and its bouncing motion combined. And so I called those radial and rotational kinetic energies. And so the radial is the one is the kinetic energy of the ball bouncing in and out, straight out. So that's going to be the change in the position over time exclusively. That's like that velocity. So 1/2 mr squared is how I got that. And then rotational is dependent on the radius and then the angular velocity. So r times theta dot is the angular velocity times 1/2 m, v squared, whatever. So that's how I got that. And then the potential energy, you have some from the spring and some from gravity. The potential energy of the spring is the stretch relative to its resting position r naught. And the equation for that is 1/2 kx squared. So in this, it's r minus r naught is x. And then the potential energy from gravity, I drew this little diagram, but there's a little bit of height relative to how far the ball has swung out. And that height is dependent on theta, r, and r naught. It's basically h equals r naught minus r cosine theta, which is what I have here. So that's the potential energy of gravity. And then the total energy is just those two summed. And when you plot these, or when I plotted this after all my work, I got that the kinetic energy and the potential energy were kind of doing equal and opposite things a little bit. I'll try and figure out how to put the plots in, probably not in this video, but I'll figure out how to do that later. And then my total energy was constant, which intuitively makes sense because there's nothing in this system that's damping or otherwise removing energy. So the total energy should be the same across all of time, and that's what I got. So there you go.